Hi everyone, my name is Sam Edds. Today I'll be talking about predicting natural disasters and testing the boundaries of computer vision. Climate change is getting stronger and stronger every year. Every year there are more and more natural disasters, and it's starting to impact all of us. From the flooding last summer to the wildfires this summer in the Sächsische Schweiz, it's really everywhere. So I wanted to see how we as an AI deep learning community could engage with this topic and whether there's something that computer vision could do. So first, a little bit about me. Like I said, my name's Sam. I'm a Z by HP Global Data Science Ambassador. So they gave me a super powerful computer with multiple GPU and lots of memory to do this project. I'm also a senior data scientist at Yelp. And I'm a big explainable AI enthusiast from my work in crime and education research and at many Berlin startups. So if this is an area of interest to you, feel free to reach out to me after. So what is the question we are trying to answer? Can we predict natural disasters in aerial images when the model is trained solely on point of view images? So a point of view image doesn't have to be directly straight ahead. It could be up, down a little bit, but right, it's from a human's perspective. And then we want to predict on aerial images. So these are not satellite level images, and this one I use is actually quite zoomed in, but these are images taken from planes, so they can actually look quite different. And the impetus for this is if we can take a model trained on one situation and apply it to many different situations, it may be easier for different users, such as natural disaster response and hazard mitigation, to implement and scale. Okay, so what does our data set look like? Our training data set has two aspects. There are these incidents, which are the natural disasters. So I looked at wildfires, flooding, and landslides. And then there are 14 different places, which are just where the natural disaster occurred. So this could be bridge, street, forest. There are a number of others that I'll discuss in a minute. And there could also be multiple in an image as well. But for the point of view images, this is less common than with the aerial images. And this data was gathered and labeled by an MIT lab. All the photos come from Twitter, so they gathered and labeled them, and then I trained a model using these. The places actually get quite granular, and this is because I'm interested in testing where is the boundary of what we can predict? How well can we predict on super granular categories? These could always be rolled up into less granular categories as well. So they're broadly think of it as 4 different buckets. There's buildings, infrastructure, land, and water. The aerial data set, there's going to be, again, the 3 incidents and the 14 places, but these are aerial images. They are not satellite level, but they're taken from planes. And when you think about a natural disaster in a point of view image, say that there's a flood and maybe it takes up most of the point of view image, or say the lower half of it. But when we think about an aerial image, especially depending on the level of zoomed out it is, it could take up a really small chunk in, say, the upper right-hand corner, and then also look quite different and have a number of different places in the image itself. So there's the potential for there to be quite a lot of difference between the image types. And this data I also got labeled from some other MIT lab, and a note to always very carefully look at your data before using it, because the wildfire data did not actually have wildfires in it, so that I ended up scraping myself. And I will let you in on one of my secrets, which is I am not a natural disaster identification expert. In these photos, they were marked as landslides, and if I look closely, I can see where there's some potential. I can also see how there's not. So in maybe 10% of the predicted photos, there is potentially not an incident because of images such as these. And this is not the case in the training data set. This is just in the data set we were predicting on. So just a little bit on deep learning. I use a convolutional neural net. So I didn't explicitly, in my case, I didn't explicitly pass in features. I passed in the image, and then it is going to assign different weights and importances to the different aspects of the image. And then, of course, there's the nonlinear combinations of the high-level features. And then the output is predicted probability. And so there's a predicted probability for the incident and also for the places. And this is a multi-label, multi-class problem, so it will not have to equal 1. But if you have more questions on that, feel free to ask me later. So let's talk about what are the results that we initially see. I think it's important to look first, how does the model do when predicting on point of view images? Because if it's trained on that and does poorly, why would we expect it to do well on aerial images? So this is really just kind of like a checkbox, like yes, it does well on wildfires, landslides, and floods. So check, it does what we expect. On places, this is a bit different. And the model correctly predicts point of view places from anywhere between 9 and 90% correctly. It does quite well on land and infrastructure. And then it generally does well on most categories. And then there are two water categories, lake and ocean, and then residential neighborhood, a building category in which it does quite poorly. So anytime the model did well, I obviously looked at the results and the images to see what to double check. And then looking at when the model does poorly, I wanted to see, is there some kind of story or pattern to understand why this could be or where exactly it does poorly. From the point of view model, one of the biggest takeaways, which when you then look at the image and think of this is a bit obvious, is determining lakes and oceans from point of view can be super difficult. So in this image, there is a flood, and it's really hard to determine that there is a lake there. I would not know this myself. And so depending on the type of incidents and the places, it can sometimes be very difficult to determine, which is a good thing to know for modeling. When we move on to the aerial images, so how does it do? I would say the results are promising. The model best predicts the fire incidents correctly, and this is 85% of the time. And because the model is able to take into account color in wildfire images, there's generally a lot of red, yellows, and oranges close together, and that's often not the case in the other kinds of images. So I think this might be why it does best on wildfires. For flooding, it is 78% and then 60% for landslides. So why might it be that landslides are much worse than flooding? Something that I noticed is that floods were often mispredicted as landslides and vice versa. So the image on your left is a flood image, and it's quite difficult to see because there's a lot of sediment that's over the water. And the image on the right, it's quite dirty. So the water is very, dark, dirty, a little bit gritty. And when we look at landslide images, when there's often water, it's often dark, and sometimes there's various aspects that are covered up by other pieces of land. And I think this is one of the reasons why the misprediction could happen. And this was a somewhat common theme that I saw. So in terms of places, aerial images often have a lot of places, and we can really see this in the results. So the model correctly predicts aerial places between 0 and 90% of the time. It does quite well on buildings and infrastructure, not buildings, on land and infrastructure. And it does very terribly on all buildings and quite poorly on most water places. So why might this be? Places in flood images are often predicted only as rivers. In this case, there actually is a river in the image, but there's also a bridge. And so when you look at the predicted probabilities, it's super high for river, and bridge is just very low. It's not that it's also high, but just the second highest. It's just that it's much, much lower. And I noticed this pattern throughout a lot of images, in that anytime that there was a river, a lot of times when there's a river prediction, there's really, maybe there is a river, maybe there's not, but there's often something else happening, and it's a flood image. And so it manages to kind of overtake, and the model's really not able to determine that something else is also occurring in the image. So that's was something that was quite prevalent. Something else is that the model really struggles to predict buildings. And when you think about what a building looks like from a point of view, you can usually see things like there's maybe a pitched roof, there are some windows, there's siding on the buildings. But when you look at a building from an aerial image, it looks super different. You can very rarely determine a lot of those features, and it just seems like some kind of small and like compressed square or rectangle. And so to me, it makes sense that it does quite a poor job predicting on this. It makes sense that sometimes, right, when you're training on point of view images and trying to predict on aerial, it's not always going to make sense. And this is also a case where predicting on, when using satellite images and trying to predict different shapes, what is a building, what is not, that already is done very well by the industry. So this is just one of the cases where it does not make sense to use a model trained on point of view images to predict on aerial for buildings. Now, this was a proof of concept that I did, and I wanted to think, how could this actually be used for public good? I see two big areas of application. One is natural disaster response. The second is hazard mitigation planning. And if we can take a model trained in one place and apply it to many different scenarios, it's going to be much easier for these agencies to implement and to work with. And right now, a lot of these agencies would not have the capacity to implement such a model, especially when we think about the amount of time it takes and technical capacity it takes to train and then implement. But if we could instead make something that is a pre-trained, give a pre-trained model, and they can upload photos to a web app, which then they're not using, they can have a normal computer, and it gives them down the predicted probabilities. So, okay, there's a landslide here, and a bridge here, and a highway here are impacted. They can actually use this information rather than if they need to train a model themselves and do all of that work. So another point of this is I trained this on about 100,000 images, so it is not very many. Imagine how long it could potentially take if you do this for millions and millions of images. For me, the GPU runtime was 25 minutes. CPU was about an hour and a half. And so again, if we want agencies to implement something, it's super nice if we're able to use something in one scenario and apply it to multiple, just in terms of their infrastructure. The same as having a pre-trained model, putting it on in the cloud, and then having them be able to use a web app for this so they can actually use the data and implementation. I have also some other ideas of what I would like next to pursue for this. I also spoke on this topic a couple months ago, but then it was summer and super nice out, so this remains my biggest area of interest to pursue, which is training with negative classes. Right now, if you give the model an image, most of the time it's going to think that there's some kind of natural disaster in it, which is, yeah, not great. The photo on the far right is my dad playing croquet, and he might be quite bad at croquet sometimes, but right, it's not a natural disaster, so it should not say that there is one. And then when we think of other scenarios, there's also bonfires and fire pits. So there is fire in the image, but right now the model is probably going to say this is a wildfire, and we don't want that to actually be the case. So training with negative classes will be able to help the model understand when something actually is a natural disaster versus when it is not. And to my key takeaways, so with refinement, I think computer vision can be helpful in taking a model trained on point of view images and predicting on aerial images. Obviously, there's a lot of refining to do. This was a proof of concept, but I think it shows that there's at least some potential. And while computer vision is computationally very expensive, if we can, in the end, make it into a pre-trained model and then give it to agencies through a web application or some other easy-to-implement form, they can actually use and scale this. And then the last is around data quality. So whatever you put in is what you get out. So if you have very biased data, it's going to be the same thing that comes out in the end. Something I noticed is most of the images I used were from summer, so I don't have things like seasonality and winter. I also have most of the images, I believe, are from the US, and so having images from other places with different terrain, etc., would be really helpful, because right now there are different biases that exist in the model as a result. So with that, thank you, and happy to answer any questions.